What's poppin', boyos? We are back in another Psychics video with Papa Bird.
Okay.
Is it coffee flavored coffee?
So this is water.
What? It's water?
So what I did is I had it in the microwave for a minute, okay? And I've warmed it up, and I'm going to put, so in here is water, it's about 80 degrees Celsius. So I'm going to put this over it, okay? And this is what's known as a Stirling engine. So I'm going to give this, which way is hot? Let's go this way, okay? So I'm going to give this a couple of spins. Now, so what's happening is that there's, if you notice, there's a diaphragm that's moving up and down below.
Yeah.
And so what it's doing is that it's drawing in warm air. Now, that warm air has a certain amount of kinetic energy, okay? And that's what temperature is a measure of that kinetic energy. Come on, okay?
It's getting there.
I know, it's trying.
What's he trying to get there, Terrell?
Sometimes it goes,
Hotter, hotter.
no, it's just a function of getting the whole system warmed up.
I'm confused. Are you just trying to get it to go continuously?
Yeah.
Okay, that makes sense.
Hotter coffee.
Yeah, she's up more.
Back in the microwave.
Microwave it with the...
Metals in the microwave don't go well.
Oh.
Maybe you need grease.
We're sitting for the next hour and a half.
No.
Just him trying to get the engine started.
Oh. Oh, here we go.
Let's go. Put it over a
Can it fly?
Poggers in chat.
Is it
Speeding up.
Is it gonna fly?
It's going now.
It's not going to go that fast. Okay?
We'll go all day.
So basically how any machine works is this, okay?
How that? That's how it works.
That's how it works.
That's pretty.
So
It's going
you've got the
faster.
piston, it's going down here, and it's connected to this diaphragm that's moving back and forth. So the short version of any engine, how it works is, here's your engine, okay? And it's going to take in some type of energy. So in this case, it's taking thermal energy from the cup. Then it's going to take some of that energy and it's going to do work with it. In this case, the work that it's doing is making that propeller spin. So that's what it's spinning part of that work doing. The rest of it just gets kicked out as heat energy. So it doesn't make any difference how complicated the engine is. A diesel engine, a gas engine doesn't make any difference. They all take in some type of energy. They do work with it, makes you go down the road, runs a air conditioner, whatever it is. Then the rest of it gets dumped out as heat. And out of this, typically, like humans, gasoline engines, whatever, typically you have an efficiency of about 25%, which means out of every 100 units of energy that you put in, you functionally only get out of them about 25. So yesterday, we left off talking about this equation, that Q equals M. What sequence do you want?
C delta T.
MC
delta
T.
MC delta T.
Yeah.
Careful. Okay? Told that to Mrs. Schertz yesterday in the meeting. She just laughed.
Yeah.
MCAT, whatever. Okay. So M's mass, specific heat change in temperature. So what I did, I took that cup and I put it in the microwave. Now, how do microwaves work, especially with water?
They just make it vibrate super fast.
Yeah, because what it does is it emits photons with a certain wavelength and energy that matches what's called the resonant frequency of water molecules. So those photons interact with the water molecules. They vibrate more and more and more, otherwise known as kinetic energy. Voila, I get hot water. So that water has a certain amount of thermal energy in it. So to calculate this, we're going to go, oh, okay, right, here's the mass of the water, change in temperature, specific heat, hey, we're off to the races. Now, a lot of times, how these diagrams play out is you'll start with this, temperature, and then energy. Okay, so we're going to kind of go through like a phase change here. So we're going to start with ice that's at minus 10 degrees Celsius, okay? And so I would say this isn't your lab final, but let's just say hypothetically. Your lab final is to take ice that's at minus 10 degrees Celsius and change it into water that's at positive 10 degrees Celsius. So I'm going to give Brooklyn an ice cube that has a mass of 0.1 kilograms, so 100 grams. Okay, y'all familiar with that? Okay, this is like, I'm not trying to melt like the entire iceberg. Okay, I'm trying to melt like an ice cube. Okay, so here's what you want to look at. When you look at your calculations of Q, you have the one that you have M delta T, right? Now, here's what's important. This is involving a temperature change. Here's your mass, here's your specific heat. You all know this one, okay? Now, there's two other ones, and I will give these to you if you need them. One is mass times latent heat of fusion. The other one is Q is equal to mass times latent heat of vaporization. So, this isn't angular momentum, okay? It's not angular momentum. It's not the length of the pendulum, okay? This is latent heat of fusion or latent heat of vaporization. So on your chart, okay, down here below the specific heat, there's a whole chart of these depending upon the solid liquids that you're dealing with. Only one we're going to worry about is water, okay? So when you look at latent heat of fusion, so do you think the latent heat of fusion is going to be involved in melting ice or boiling water?
Wait, no, melting ice. No, wait.
Why?
Because you're reversing the fusion of water stuff.
Yeah, fusing, right, means that you're going to put stuff together. So latent heat of fusion, that's going to be dealing with solids to liquid. Vaporization is going to be with boiling or condensing. So I've got ice that's at minus 10 degrees Celsius. So if I'm going to melt this stuff, what do I have to do? Warm it up to what?
0.
0. Because it's not going to melt until it hits 0. So here's what's going to be important on this. I got ice at minus 10, and I'm going to begin to dump energy into this system. And I'm going to warm it up to 0 degrees Celsius. Now, is there going to be a temperature change?
Yeah.
Yes. So what's happening is that I've got water molecules that are locked in place. This is solid ice. And those are pretty strong bonds. If you've ever tried to break like an ice cube, those are pretty strong bonds. So we're going to put this energy in, and we're going to make the particles vibrate, but we're not going to break, okay? We're just going to warm it up to 0. So in this situation, to get this amount of energy, I'm going to redraw this and start over so we've got more room to write. So I'm down here at minus 10 degrees Celsius, and I'm going to warm this up to 0 degrees Celsius, right? I'm going to dump energy in. So anytime you change the temperature, you're going to use Q equals M, which in this case is 0.1 kilograms. Now, here's what you have to be careful of. This is ice. So you've got to come up here and you've got to find the specific heat of ice. Don't use the specific heat of liquid water, okay? You've got to use the specific heat of ice, which in this case is like 2100 joules per kilogram degrees Celsius, and we're going to warm that up 10 degrees. So oddly enough, conveniently, I get 2100 joules of energy. So that's how much energy that I have to dump in to melt this, to warm this ice. This isn't to melt it. This is just get it up to where it could possibly melt. So if you consider this is like 10 newtons, that's like lifting this thing up 1 meter and doing that 210 times. That's how much energy it's going to take, if you kind of visualize that, to take an ice cube and warm it from minus 10 to 0. Now, here's what's important. At this point, this line plateaus out. So what that means is that we're still going to dump energy into the system. And here's what's important. We're going to dump energy into the system, but we're not going to change the temperature. That energy has to go somewhere. So where do you think the energy is going? It's got to go somewhere. It's not making it vibrate. What is it doing? What's the difference between solid ice and liquid ice? Which one do you think has more hard, solid bonds? The ice does. So I'm going to get this thing as liquid water, so that energy goes to break the bonds that hold it together as a solid. So this is going to be QL. Q is going to equal mass times your latent heat of fusion. Now here's what's important. So when you look at your heat of fusions and vaporizations, look at the units. Notice that there's no degrees Celsius on here. The reason that there's no degrees Celsius in there is because we're not changing the temperature. That energy is going to either break bonds or form bonds. So in this case, I'm going to take 0.1 kilograms, and then latent heat of fusion is 3.33 times 10 to the 5th joules per kilogram. So here's what's important. You get kilograms to cancel out. There's no degree Celsius, because this is the energy that it takes to break the bonds within a kilogram. I'm not changing the temperature, so I'm not changing the kinetic energy. What I'm breaking is the potential energy that's held within the bonds of the water molecules. So if I do this, I get 3.300 joules. So at this point, yes?
Sorry, so why are we using latent heat of fusion and not latent heat of vaporization?
Because vaporization we're going to use later when we talk about boiling water.
Oh, okay.
Okay? Now, so I got this latent heat of fusion. Now, so here's the deal. And this is important conceptually. Let's say I wanted to reverse the process. Let's say I gave Brooklyn her lab final and said, Brooklyn, I'm going to give you water at 0 degrees Celsius that's a liquid, and I want you to change it into ice. So Brooklyn, what would you do? What would you do to take away the heat? Don't make this difficult. Where would you put the water?
No, in some place cold.
Yeah, perhaps a freezer.
Yeah.
I'm just throwing that out.
I mean, I'm trying to be open.
I know. Or you can take it to the North Pole where Santa is. Okay?
Okay.
Yeah. You can rock that.
Hey
little
Santa,
bit.
can you use your freezer?
Yeah. So,
Take your freezer too.
but here, and this is an important conceptual idea. When she puts that water in the freezer or takes it to the North Pole, whatever the case may be, is she adding coolness or removing heat?
Removing heat.
You're removing heat. So you never add coolness. The only thing you can do is remove thermal energy. So that's what happens when you make ice. Now, at this point, I've taken ice that was a solid, and I've added energy to it, and now it's a liquid. Now, liquids are actually, if you think about it, liquids are very rare. Okay, seriously. No. Other than water-based substances, bodily functions, drinks, whatever, even milk, what other liquids do you encounter on a daily basis?
Mercury. Daily.
On a daily basis.
I mean, I eat
Blood,
fish.
my veins.
That was mercury.
Yeah,
Liquids.
Okay, let's see.
it's not solid, is it?
So seriously, think about that.
Glycerin? No.
On a daily basis, what are the two forms that you encounter most often?
Water.
No, just in general. Solids, liquids, or gases. Which ones do you encounter most often?
Solids.
By far and away, solids, right? Now, but what also do you have to exist?
Gas.
Yeah, so without an atmosphere, guess what? We're kind of screwed. So, most of the stuff is solid. Your clothes, the table, your hair, your comb, whatever it is. Okay, yeah, you might use hair gel. Okay, kind of a liquid. But here's why liquids are so rare. You have to hold the particles together so that they can move past each other, but they don't exist as a solid structure where they're locked in place, but yet you have enough bonds where they could slide, but yet the bonds aren't so weak that it turns into a gas. So if you think about it on a daily basis, you don't have that many interactions with liquids. Most of the stuff that you encounter is solids other than this layer of atmosphere that we have.
It's the Goldilocks.
Kinda, yeah. Now, so here I've got water at 0 degrees Celsius.
No.
What?
Why is there so much water then? Like,
That's actually one of the big questions. Is like,
there's
where
so
did
much
all the water
like,
come from?
everywhere.
Yeah.
Where's the water?
Okay, so why?
Water?
Where's my water?
Why? Okay.
What's going on with the water, dude?
At this point, I'm going to boil the water.
Yeah.
Okay? We're going to go right through 10 degrees. We're going to go straight to boiling water. So at this point now, here's what's important. I've added energy, but I didn't change the temperature. So now I'm going to boil the water. So I'm going to add more energy, but now that energy is going to go to change the kinetic energy in order to increase the temperature. So in this case, I'm back to going Q equals M delta T C to P. I've still got the same mass of 0.1 kilogram. What's going to be my change in temperature? I'm going to go from 0 up to,
10. What?
Would be
I'm going to make the boil, so we go
Oh,
all the way
100.
up to 100 degrees.
100.
But now I'm going to use the specific heat of water because now it's liquid water. And that specific heat is 4,186 joules. So if I take 100 times 4,186, I get 41860 joules. So about 400,000 joules. So here's the deal. It only took me 2,100 joules to raise that ice from -10 to 0. It took me 33,300 joules to melt the ice. But it's going to take me 418,600 joules to raise it up to 100.
would you have to multiply by mass?
Yeah, but okay, I'm off by 0, because that's right, because it's 0.1 kilograms. So I'm off by 0. Hold on. Good catch. So 4186. So
Let's go, Jacob.
Yes.
Let's go, Jacob.
Wait, now it's 6
What did it say?
4,000.
8.6.
It
It used to be 416,000.
Okay.
Now it's 400,000.
Yeah, because that's 0.1, so we're down to 10, so 41,680 joules. Okay? Now, at this point, what's the water going to start to do? Boil. It's going to wiggle a lot. But now, it's going to wiggle so much that we're going to break the bonds that hold the water molecules together. So here's what's important. The latent heat of fusion of water is 3.33 times 10 to the 5th. The latent heat of vaporization to boil water is, what is it, 2.2? No, it's 22.2?
6.
22.6 times 10 to the 5th joules per kilogram. So here's what I want you to look at. Does it take more energy to melt ice or to boil water?
Takes more energy.
Boil water.
Yeah, it takes like an order of almost 10 to the magnitude greater to boil water. So now, to get that energy, I'd take 0.1 times 22.6 times 10 to the 5th, I'd get that energy. Then if you wanted to heat up steam, so this line would plateau out, and then you'd have steam, and then you could heat up the steam. So this is how you typically generate electricity, is that you have, and it's horribly inefficient, so you take a big vat of water, and you take coal, natural gas, whatever it is, or a nuclear power plant,
Yeah.
and you boil that water, right? And it changes it into steam. Then you take the steam and then you heat up the steam, okay? And now you've got individual water molecules that are bouncing around on steroids, which is a tremendous amount of kinetic energy. And then you ship them out and they hit a turbine. Turbine spins, that's hooked up to an electrical generator. At the end of the day, we can make toast, okay?
Yes.
That's how all electricity stories end, is that you can make toast. But here's the problem. This takes a lot of energy because you've got to heat up the water, boil it, heat up the steam, and that takes a tremendous input of energy. Then you're going to hit the turbines, and then that energy is going to get changed into electricity. But then the water is basically wasted because now when it hits those turbines and makes it spin, that water is going to lose that energy, and then it's going to begin to condense back. So in the best case scenario, you can take that water and loop it back in. So it warms it up, Dr. Bob. So you can take that steam, spin the turbine, You generate electricity, we make toast. But the problem is that this takes a lot of energy just in that process, and you go through a lot of water. So here's the beauty of the voltaic cells. What does the voltaic cell eliminate? Out of this whole process, what does it eliminate? Water cycle. Okay? As water becomes more and more of a limited resource, that's the beauty of photovoltaic cells, is that you go directly from that solar panel directly into an electrical feed without having to go through that whole process of heating up the water. So like our system should, in round numbers, save about like 60,000 gallons of water a year, okay, based upon the electricity that we're going to generate without going through all of this process of wasting that water. So that's another advantage, is that you get a direct conversion of this. Now, here's always the knock on whether it's wind, whether it's solar, whatever, is that, well, it's great if it's sunny, but a lot of times you need that electricity at night. So everybody says, oh, build batteries. Well, here's the problem. Those run on lithium ions. Lithium is a very, very scarce resource. So there's one company that's pretty clever. What they've done, they've got a couple of these set up. It's an automated system where you have a big crane that's up here. And it's up here, and what it does is it's fully automated. And so you set this up around a solar farm or a wind farm, whatever. And so what happens is that when you have excess electricity, the electricity flows up to the electric motors in the crane. The electric motors in the crane grabs a hold of these big, massive concrete blocks, and it stacks the blocks, storing what type of energy? Potential gravitational energy. So when you have excess energy, it's storing these and it's lifting up these blocks. So it's building this like cylindrical area of big, massive concrete blocks, because a lot of times you have excess concrete, you don't know what to do with it. Oh, here, let's add these. So that energy is flowing in this direction, and you're storing this as gravitational potential energy. Then at night, what do you think they do?
Just let it fall.
Yeah, so then they're going to let these fall back down. Then those electric motors spin in the opposite direction, and then you're generating electricity that's going back out onto the grid. So you're storing energy not as in a battery, but you're storing it as a mechanical system. Okay? So you're still storing that X amount of energy, but this is actually much more efficient in terms of what you're going to lose than batteries are. And the beauty of it is, hey, what are you going to do? Okay, we've got big concrete blocks that we don't know what to do with anyway. Let's use them to store energy. So then, like at night, you can reverse this, dump that energy back out onto the grid. There you go. So, go with that. All right. Now, to show you that gases can contain energy, whether it's steam or whatever. So, come back and
We're going on a trip in our favorite rocket ship, zooming through the skies. Little Einstein. Oh, my bad. Oh, sorry, go ahead. Oh, boy. Get ready to explore. They don't need the high. Little Einstein.
Also great.
okay. Well, they saw it yesterday, so. All right. So what I'm going to do is I'm going to take a little piece of cotton and put that in here. And then I've just got this plunger that goes over that. Okay? I'll get this pushed down. Now, we're pushed this down. Am I doing work?
Yes.
Why?
Force
over distance. Now, when I let go of it, what's going to happen?
It's going to shoot up.
It's going to go back up. So here's the question. Can the gas inside of that do work?
Yes.
Yeah, it just did, right? Okay. Now, which actually is easier to do from a gravitational standpoint? Push it down or push it up?
Push it down.
Down.
Why?
Gravity's working with you.
Yeah, gravity's helping me. So what happens is that you take the nitrogen and oxygen molecules and you're condensing them. And they don't like that. So they kind of freak out and go, bad, right? So as soon as I let go of this, what happens? What does it do? It's going to take that energy that's stored, okay, and that's basically what you're doing is you're storing potential energy. So you can think of this as being like a spring. So when I push this down, I'm storing energy as like a gas spring.
Does it work like a spring, like in terms of like energy?
To a certain extent, yeah. Okay?
Okay.
So, but you're storing it, and then you can calculate the amount of work that it does. So you can calculate that force over that distance and how, so if you knew the weight of this and you knew how far it pushed it up, you could calculate the amount of work that was done.
Yeah.
Just like in the same instance as if it was a spring, that was lifting up an object.
Yeah.
Same idea.
Could you calculate a spring constant?
For
For-
yeah. And so these particles don't like to be together, so they're going to go, "Poof, I need more space, get away from me." All right. Now, if I do this very, very slowly, okay, not a lot happens, okay? But what I'm going to do is I'm going to do the same thing, I'm going to do it very, very quickly. So this is analogous to striking a match. If I strike a match and pull it across very, very slowly, it doesn't ignite because of the fact that I'm giving it time for that thermal energy to escape. So I'm going to do this, but I'm going to do the same thing. I'm going to do it very, very quickly. Okay? Come on. Hold on.
Oh, I know what this is.
Hold on.
this in camp.
I remember this now.
Oh, it should. And it's one of those deals, it works until the principal is in the room, and then it doesn't. Okay, let's try that. Hold on. We got smoke.
Maybe can we
No
shut
smoke,
the
no
lights off so we can
smoke.
see it better?
Can go on it. I can go, won't go.
It's like vaping in reverse.
No smoke.
Yeah. Hey, Joe, why don't you tell Dr. Botts your complaint about the bathroom?
There's an ongoing joke about how they keep putting toilets in the jewel room.
I'm sorry, I shouldn't find
That's funny.
Yeah. Okay, I was like, what are you doing putting toilets in the jewel room? I know that's horrible. I laughed pretty hard, and I probably
Makes
should.
me laugh.
Okay, so hopefully this one works. Okay, so
Prometheus.
if you look at what happened
You discovered fire. That
around
was.
the edges,
So this is how the cavemen did.
so you'll notice around the edges that it looks like it's singed, okay, like you'd held this over an open flame. So here's the cool thing about this. So there's no accelerant that was added. It's the same nitrogen and oxygen molecules that you all are taking in right now. But if you take those same molecules and you compress them very rapidly, they flip out. And they gain that energy, and they gain so much thermal energy that it acts as like a fire. And so it's the same idea, but what happens, but here's the question. Why didn't it ignite when I pushed it down slowly?
That energy had time to escape.
Yeah, you were giving it enough time for that thermal energy to escape out. So this is how diesel engines work. So diesel engines work by a compression. So you take diesel fuel, mix it with air, and you have a very, very high compression ratio where it comes in, hits that ignites, and then it drives that piston back down. And so that's what happened here. When I pushed that down, it ignited. You had a rapid expansion of gases, and it just didn't push it up. It like pushed it up all the way out. So let's try it without. We'll try it without the lights as an added effect. So somebody, when I tell you to.
And no one's back here yet.
Huh?
Nothing.
Nothing?
So loud.
Okay.
Forget to like and subscribe.
Like and subscribe. Okay. You ready, Michael?
Oh.
Hold on.
You gotta do it for the subscribers.
Got to do some for the subscribers.
Do it for
And they're
the-
going, why should we like and subscribe?
No, you can just edit out.
This is why.
It's really not working.
First try.
We'll fix it. Well, don't worry. We'll do it as part of the compilation.
We'll fix it in post. First try.
Maybe she hit harder.
One more time. Hold on. I can't hit much harder without breaking my hand.
Break your hand.
I'll do it. I'll do it.
For the kids.
Do it for the subscribers.
Typical principles.
Do it for the subscribers. Don't worry about the children. It's all about the subscribers. Patrick Fletz watching from K-State.
Yeah, actually.
Yeah, he watches them every once in a while when he gets bored.
Make sure you comment while you're watching. People when they complain about it, they're like, I can't play guitar because
Here we
my
go.
fingers are too small.
I have made fire.
Prometheus.
Start natural fire by using
No, because it just burns out so fast.
Yeah.
Don't do it in
Okay.
California.
Got it. Good. Grand. Back
We're
together.
going on a trip in our favorite rocket ship, zooming through the skies. little Einsteins. I'm on board. Ready to explore. There's no need to hide. Little
We're gonna
Einsteins.
take the footage of him like blowing it out, reverse it.
Does it work here?
What?
So like in that demonstration, is the reason why like it doesn't, the flame doesn't like, why it extinguishes because like the oxygen.
Yeah, you basically use up that oxygen so
Okay.
fast. These election notes will flip out.
Yes, I love lecture notes. Lecture notes are my favorite.
That's today.
So we're gonna take the footage of him blowing through that thing, reverse it so it looks like he's hitting the jewel.
What?
I have bending pencils.
What?
Actually, I have it in my bag.
I just got really
So
excited.
actually, the alternate name is our cheap pencils that bend.
And he told me not to freak out election notes.
I'm not running it. Bright orange. I'm gonna run it. What's it called? Because I'm not driving all the way to Sunset.
There you go.
Miss me with that.
Thermo.
So we might not run what we're supposed to run either.
Okay.
So that weird
Yeah,
workout.
thermo.
Miss me with that.
So,
No, it's like 2 miles at a minute slower the race pace. Plus
Thermo
15,
turbo.
plus 15 by 15. Yeah. Yeah. It's like 2 miles at minutes slower than race pace. Then 15 on, 15 off at 2 mile race pace. And then another 3 miles at a minute and 30 below race pace.
30 minutes. Oh, baby, you got a deal.
Wait, what?
30 minutes below race pace?
No, 30. A minute 30. You just walk. You walk backwards. It's like you go negative mileage.
Run 0.9.
Are you proud that, hey Joel, are you proud that you've now told bots your joke?
I am.
Yeah.
I can't tell if you actually want me to tell the joke or not, so I kind of just did.
Wait,
Okay.
is it full?
so what you've got here is this whole idea of a bunch of definitions and things like that. So they only kind of make sense once you kind of look at it in terms of an example. So on the back of the notes, you've got 3 distinct processes, okay? Isothermal, isobaric, and isovolumetric. So for those of you that, if you remember back from your freshman science days, what do you call lines on a map that connect lines of
Isobars.
equal pressure?
Isobars.
Isobars, okay? What do you call lines that connect equal temperatures?
Thermobars.
Isotherms, right? So iso meaning that something's going to stay identical,
It's
right?
the same.
Oh, it's the same.
Same.
Okay. Now, so here's what we're going to do. What we're going to do is we're going to look at this pressure volume graph, and it's one of those deals, once you think your way through it and you look through some examples, then it all becomes pretty simple to work off of. But it does require some thought. Okay, I'm just going to preface this right now. It takes some thought. Okay? Just fair warning. Okay? So don't flip